And the title of my thesis is Joint Design and Applications for Devices with Expanding Motions. So there's a little bit of an outline. I'll first go over some general background about those expanding motions, and then go over three main categories of my work, the origami ballistic barrier, and then cylindrical developable mechanisms, which is a mouthful, so I'm going to call them cylindrical DMs from now on. And there's a motivation there behind that study, and then the two sections in there are surgical device concepts and then joint design for those cylindrical mechanisms. Then I'll have a general conclusion of the result of my thesis work, and then contributions, acknowledgments, and times for audience questions. So, as a general overview, expanding devices is in the title because the work involves both origami and these new developable mechanisms. But in general, these devices have the ability to expand, multiply their size almost, or footprint to a specified state that has a certain amount of characteristics and qualities that you designed it for, and then collapse back down to a certain, often a flat state in origami, or to a certain shape with the developable mechanisms. So I'm going to move right into the origami-inspired ballistic barrier. So the work was inspired by, the barrier itself was inspired by previous work done by Kyler Tolman on thick folding origami. And this design of his looked somewhat like a barrier, and that led towards the design of a bulletproof version of the barrier. But when I came into the project, I had this canvas non-bulletproof model to work with, and my work was to get it into a bulletproof version and design the joints and actuation methods for that version of the barrier. So some requirements that we set forth for it with Jeff Niven, and also by calling my dad as one of the police officers, was we wanted to have it meet a 3A ballistics rating, meaning it could stop just some large handguns, deploy really quickly, be self-standing, be stable enough to stop a brick or rocks being thrown at it, relatively light, being used by a single person, and then shield about 3 people and fit down to the size of a spare tire so it could possibly fit in a trunk. So in a quick summary of the construction of the barriers, so you'll understand the full stuff later. But there's rigid center panels that were shaped to create the origami pattern. They form the facets or the rigid part of the pattern that doesn't bend while it's folding. And then there's a continuous membrane of Kevlar fabric, which makes it bullet resistant throughout the whole surface area without any weakness in the joints. And it's a total of 15 members of a composite layup. And sneak peek, all the design requirements that we made were either met or exceeded. So a lot of my work was in the design of the joints, and originally the thought was to use some type of a membrane fold because we have this fabric that can act as a membrane. We've got to have 12 layers of that fabric to be able to make it bullet resistant. So the original idea was to use a sewing method called bunching, where you kind of bunch the fabric together with the joint so it then has room to expand around corners when you fold it. And that evolved through a series of projects and testing into the center panel design, where the rigid panels in the middle have a space between them to allow the fabric to bunch into the space, and also to allow that joint to either fold around other panels or fold in on itself. So the space between that is defined by the thickness of the material, and also whether or not it's sandwiching other layers as it's folding. And that resulted in us being able to use these vertices with the 12 layers and the ballistic nylon or black nylon that sits on the outside. And the pattern progressed twice with my help while I was working on the project. And this is the original canvas model pattern that folded into a circle to really closely resemble a spare tire. But we decided to cut off the exterior vertices to make it a simplified pattern that actually provided more horizontal coverage and less side coverage, with some decision made with some Homeland Security input. It also made it a lot easier to fabricate because we had, decreased the number of folds or vertices, by half. And then the final version actually happened quite recently with some input from Joey Eddington, an industrial design student who came with us with a folded pattern, and eventually made this little hard model and said, "This is a really good idea." I'll pass that around. But the main contribution is to change all of the majority of the creases to be vertical, which is more stable against the pull of gravity. It also allows all of the panels to be accessible from the outside, so we can roll up the fabric and sew it with a sewing machine, and then unroll it and then slot in the rigid panels. That also means you can change them out to a different material to potentially increase the amount of bullet resistance you have, maybe some assault rifle rounds. And I took a picture from the back because you can see there's no hardware needed to support the barrier. In previous models, there was a series of gas springs, or 2 gas springs that actuate to keep it up. This one, it's self-stable, doesn't need any actuating hardware to stand on its own. So the conclusions of the barrier, thickness accommodation techniques can be used to adapt origami design to unique fields like, bullet-resistant barriers. And then the membrane fold technique can be modified for membranes much thicker than the panels themselves. Traditionally, it was just thick panels and a thin, flexible membrane, but we swapped that design. And then the benefits of origami with proper joint design can make large-scale effective solutions. The next section is all on these cylindrical DMs, or developable mechanisms. So I'll go over first a little bit about what those are, and then do some motivation for why we're studying these, or why I studied these in a certain field. So developable mechanisms are mechanisms that emerge from and or conform to a developable surface. And these are the 3 main types: cylindrical, or general cylinder shapes, conical, and then tangent developed, which Todd is smart enough to study, but I did not touch because they're very complex. But yeah, there's a summary slide there. So the cylinders can look somewhat like an unrolled cylinder, and the cone can look like an unfolded cone, but that's the general idea. And so these mechanisms work, and their main feature is that the axes of the joints all line up with these ruling lines, or flat lines, or straight lines that are fit to the surface. And that allows them to take on unique properties. But I'm focusing on cylindrical mechanisms, which are planar mechanisms, or the traditional 4 bars that you think of, often will fit well to cylinder surfaces. So, and why am I doing cylinders? Well, in the medical field specifically, because in the medical field, if you go to a doctor's office or the surgery room, cylinders are everywhere. You can see that there's catheters, syringes, and needles. There's laparoscopic devices, even the stethoscope, tubing. It's all cylindrical. So there's a lot of cylinders we can fit to there, but also specifically these laparoscopic devices are very complex, have dozens of parts, and they're very small. And they want to get a lot of complex motion and control out of with a lot of parts. So the hope is that, or the desire is that we could use these relatively simple mechanisms to achieve the same type of motion with a lot lower part count, which makes them cheaper to produce and simplifies the control of them. You don't have to worry about 17 different parts. You just have to worry about the 4, parts that you're controlling for. So the first thing I did, I won't talk about this, it's too much text to go over, but is to characterize the properties of cylindrical developable mechanisms, cylindrical DMs. So I broke them down into behaviors, characteristics, and functions. The behaviors being kind of like the base motion, or I guess behavior, right, of the mechanism. So predictable motion, emergent motion, provides energy storage, things like that, just kind of base properties of it. And the characteristics are more descriptive, that could be used to fit it into a certain category. So some of these are formed from the definition of developable mechanisms, but a few are independent, like potentially enabling monolithic designs or enabling a sheet material construction. And then functions are the verb that you want your device to accomplish: cut, suture, that kind of thing. So I mapped these behaviors to the design process for these mechanisms. So I noted that the behaviors that you want your mechanism to exhibit dictates the required energy and motion modeling. So if you want to have a bistable behavior, you need to then look into energy modeling to achieve that behavior. And then the characteristics that are not inherent to developed mechanisms dictate the geometry, the linkage, and the manufacturing options for your mechanism. So if I wanted to have something that was made of the sheet material, I'd have to make sure that I could stamp the pattern out and then roll it into the cylinder, it would then behave the way I want it to. And the functions that you want drive the shape of your links. So if you want something to suture, you better have a needle in there, and that's part of your links, part of your linkage. So I'm going to go over 2 example devices that were produced during this work. This first one is the internal scissors. And what we wanted to do was have something that cut on the inside of the cylinder. So these very small laparoscopic tubes used to perform surgery, we wanted to have a blade that cut or grabbed on the inside, internal. So the desired behavior then was internal motion, moving inside, and then relative motion. We wanted the links to move past each other for a blade or a grating motion. And that drove the mechanism design so that the orange and the blue could pass each other. The desired characteristic was the conforming nature, so those links then have to be pushed out to the cylinder wall. And you'll notice that there's also 2 rings or cylinders in the final design. We wanted to have a tube-in-tube actuation, so you rotate the inner cylinder to actuate the mechanism. So you can play with this one as it goes around, but you rotate the red tube to actuate the decisions inside. And then the desired function was cutting, so the orange and purple links were shaped to be in a blade, and the purple was extended beyond its connecting pin to have a blade that passed the rest of the orange link. So pass that one around, and it's a little guy on the inside, but you can see it. So just spin the red thing. So this is what it looks like. Quick little video that BYU photography did for us, but this has a lot of potential benefits for surgical applications. We've talked about the design with a few surgeons, laparoscopic surgeons specifically, and other general surgeons. But they like the idea that this could be used for biopsy samples, to be able, you could potentially insert a gripper like you see in the video, grab a piece of tissue and retract it partially into the tube, and then cut off and contain that sample and remove it from the body. And then another idea was, another thought was that this could be used for morcellation, where they're trying to go in through their 1-inch minimally invasive incision and remove a tumor that's larger than that. So they could break up into pieces and contain each piece rather than breaking it up separately and potentially spreading the tumor out to the body. So it does show promise in that field. The second design is the multiplying cylinder device. Oh, let me pass around this thing that you saw. If you spin the blue link, you can see that scissors actually get more of the motion there. So the multiplying cylinder, as you can think from the name, but the cylinder actually itself multiplies into multiple other cylinders. But so the desired behavior was, translation, get the cylinder away from the other one, and then emergent motion, have it emerge from the side of the cylinder wall. And same desired characteristic conform to the wall, so we push the links out to the edge of the cylinder wall, and then the desired function was to expand, multiply the space available, and potentially observe, maybe mount in a camera to move away from the laparoscopic tubing, and then insert another instrument, have the camera be off to the side of that. So that drove the shape of the orange link to house whatever other tool you wanted to channel or use at the end of the shaft. And again, there's the blue mechanism. So this is a few, I guess technically, well, 2 versions of the multiplying cylinder device. You'll notice in the bottom right there's the blue cylinder where it's been demonstrated that the cylinder that expands off of the original tube can be elongated to potentially act as a second channel to introduce an extra tool or fluid or bring a vacuum in. So the thought was you enter through a space and then expand to have now 2 working channels. This is a prototype that you see here. Unfortunately, the lights are no longer inside or functional. They have their fatigue limit reached and the wire snapped off. But this is fun to play with, so I'll pass that around too. And then I'm sorry if you're a little squeamish, but it's just an example of how it would potentially look inside of a surgical space. Have the cameras emerge off and then allow 3D vision. Okay, so last topic is this joint design for cylindrical developable mechanisms. The goal of this section of the work was to try and find available compliant hinges that could work for cylindrical mechanisms, and then find the promising ones and create models for those designs that would further enable iteration and analysis on those prototypes for those designs. So the motivation is that as laparoscopic tooling companies are discovering, when you get down to their small 5mm, 3mm diameter tubes, it's hard to get pin hinges that work at that scale because they become so small that they break easily, they're hard to assemble, it drives up costs because you're manufacturing such small parts in large quantity. So the thought was that a compliant version of these mechanisms could simplify the scaling, reduce cost, simplify or remove the assembly process. So that's the motivation for this part of the study. But a bit of a background section. I'm going to be discussing the pseudo-rigid body model. So as a bit of a background, this is an alternative model for compliant beams. It allows you to replace a flexible beam with just a pin joint and some resistance to that pin joint, or a torsional spring at the same location. So you can see the two simple versions of this that I'll be adapting to cylinders and discussing their issues is the small flexural pivot, where a small flexible section that's short in length compared to its rigid counterpart is replaced with just a pin at the very middle of the flexible section. And then the initially curved beam, which is a long beam, it's not small in length compared to its rigid portion. It's replaced with a pin joint some distance away from the wall of the rigid mounting, but it can sometimes sit off of the actual portion of the device. So some issues for modeling these in a curved or cylindrical mechanism. For the small flexural pivot, the one on the left, is that the pivot itself would have to be curved, as would be the rigid link, to fit to that cylindrical surface. But the only, according to my knowledge, the only available model for the small flexural pivot uses elliptic integrals, which, as many of you know, are very difficult to use and even harder to get into a computer program for analysis. And then the initially curved beam, as I just mentioned, sometimes the pin joint is actually off of the surface of your cylinder, and that can change the length of the links, and therefore potentially change the type of mechanism that you want to use in your design, so that has to be accounted for. And also it has a limited amount of motion. So if the existing model is only valid until this curved beam again becomes flat. So if you're trying to so this is the multiplied cylinder design with two compliant joints. But if you're trying to merge away from the cylinder, that link becomes uncurved, I guess, opens against this curvature. And the model's only valid until it becomes flat, which means we can only analyze this mechanism until it reaches that state, not all the way through its actuation. And then there's no pseudo-rigid body model that I'm aware of for forces and moments at the end of a curved beam, because if we apply the force at the end of this rigid section, it would also produce a moment here, and we have to have a beam model as well. So another potential link type or joint type for these mechanisms is the membrane fold, which in traditional origami work uses a thin membrane between the rigid panels of the origami to provide a almost zero resistance joint between the two rigid panels, kind of like the barrier. And there are possible medical applications for this, medical manufacturing options. A lot of catheters and flexible instruments of that nature that are inserted in your body are coated in a certain polymer, and it was thought that the polymer, if modified in the right areas, could become the membrane for this cylindrical mechanism. But, as I'll explain with this handy diagram on the top right, it also has that issue where the pins shift away from your original location you desire them to be. So if we have our fixed cylinder with a zero thickness cylinder inside, we usually model the pin joints to be on that surface, but if we want to use membranes, we have to adhere a membrane to the outside or inside of the cylinder, and that causes the shift the joint locations to the outside or inside of the wall, which forces one of the links to change in length, and that again can alter your mechanism type and the classification of your mechanism, so that has to be accounted for as well. Questions there? Okay. The last joint I'll discuss is the lamina emergent torsional or LET joint. It's a pattern cut into a laminar or flat material designed to change its longevity or stiffness in a certain direction, so you can create almost a joint motion. And curved LET joints were analyzed previously by Jared and Trent Zimmerman, but the goal of this work was to show that LET joints in thin-walled cylinders can be modeled as if they are not curved. Just use the same planar equations to model them. The motivation behind that was to simplify the modeling process and decrease simulation time so that we can do more faster and easier analysis on these thin-walled curved LET joints. I also want to acknowledge Pietro, who helped me with this portion of the research, and I would not have graduated on time, nor would my work have looked as good if he was not here to help me with it. So very much thanks to you. So first I want to show that modeling these curved joints as flat would be even useful, or want to validate that we further design or further analysis would be beneficial. So a little bit of background. The LET joint here is modeled as can be modeled as a series, well, springs in series and parallel. And the torsional beams that I'll keep mentioning are K1, 2, 3, and 4, and they're the joints that the beams get twisted in torsion as the link, or as the let joint bends. And they provide the majority of the deflection in the let joint, so it was postulated that if we could show that their stiffness was similar to the stiffness of a flat or planar let joint, that further analysis would be beneficial, because that drives the majority of the deflection. So what I did, there's a lot of big similar words here, so forgive me if I stumble, but I compared the torsional constant for the torsion beam of a annular or curved let joint to the torsional constant of a planar let joint with the same cross-sectional area. Okay. So torsional constants of the torsion beam cross-section with the same area between curved and planar. And for the ratios that we wanted the thickness to radius ratios that we were working in at the small scale that we had, all of the errors, assuming that the planar torsional constants were the true values, were less than 1%. So this validated that further analysis would be beneficial. So with Pietro's help, we went full bore and analyzed the analytic planar models compared to FEA curved models of let joints, then again compared to 3D printed curved joints. So the analytic equations were developed previously. It's a relatively simple series of fractional equations designed to get you an equivalent stiffness of your let joint. And so the same 10 or 15 joints that were analyzed in FEA and experimentally were also input into the planar equations without their curved radius. And this is Pietro's script that he's been developing previously and then graciously modified with me to work for these curved let joints. But he creates the geometric parameters and material properties and everything in MATLAB, and that gets imported into ANSYS to make the model, mesh it, apply the loads, find the solution, determine equivalent stiffness, and then bring it back into MATLAB for plotted against the other results. So to explain the experimental, what we did was find the modulus of a particular, of PETG, which is a water bottle plastic, but 3D printed PETG, and then use that modulus in the other models to compare, and printed let joints with the same dimensions modeled earlier, and found the deflection path in FEA, which is the x's, and it's not a perfect circle, but we approximated that path as a circle and designed a control arm that would deflect the let joint along very close to that path, and used a guided rotation to get the torque applied to the let joint, and using a laser encoder to get the amount of deflection. So we have the torque gauge, the laser encoder, and then our 3D printed let joints and our control arm that guides it along the path that it would deflect along if it were loaded with the pure moment, as it was in FEA. And the results of this were quite satisfactory. The FEA model is of the curved let joint is the blue triangles. The green is the experimental or 3D printed parts, and the planar equations are the dotted line. So the FEA experimental fit quite nicely for a 3D printed sample, which validated that FEA model. And then the planar equations are relatively close to the curved models for our range of thickness to radius ratios that we're in. So that was very, very good news. But there are some weaknesses of the previous model. It does model linear material deflection, so linear amounts of stress strain. And but the expanding cylinder, I passed around the memory. Sorry, there we go. The expanding cylinder device has a joint that goes through 90 degrees of deflection. This one here. So I just fell apart. I wanted to show that these mechanisms could exist with let joints if you used a more exotic material that went through large amounts of strain. So what I did was model the expanding cylinder device with let joints and ANSYS using these rigid beams on a pivot to represent the inner cylinder that drives the outer mechanism around the outer cylinder. And this design was iterated on with 33 different models, and the best results show that the stresses and strains obtained in the 90-degree let joint deflection most likely would not produce yielding in a nitinol, superelastic nitinol device. So, So some conclusions on the cylindrical development mechanisms. They are promising for laparoscopic tooling based on the devices that we created and the feedback we got from multiple surgeons. And also the membrane joints are potentially viable for cylindrical DMs in the medical field. And the planar modeling assumptions for the torque displacement of LET joints as if they were planar was evaluated and shown to be useful. And also, lastly, the LET joints with exotic materials may enable low part count cylindrical development mechanisms to exist in the medical field. So to wrap up, I'm going to go over just my general conclusion over my thesis, and then go through some contributions to the lab and acknowledgments to those that are in the room and some that are not in the room, and then have time for questions. So, majorly, proper joint design origami is key to getting origami and developable mechanism-based devices into engineering applications. And this work advanced origami adaptation and DM joint design in 3 different design stages. So first, which the work was also done last, but simplified the model for using curved LET joints and modeling them as if they were planar. And then showed functional prototypes for these laparoscopic devices and gathered feedback on their uses. And then also finally a tested product, which is the ballistic barrier that we tested at a firing range and showed that it should pass the qualifications for a 3A barrier. So my contributions to the lab, 4 papers, 3 that I authored, 1 that I co-authored with, but the ballistic barrier paper was published at 7 Osme and presented in Oxford, UK. And the cylindrical surgical devices that passed around the room, the paper was written on those, and it'll be accepted, or it was accepted to the DETC 2019 conference to be presented by Dr. Hal in Anaheim in my absence. And then the last paper on the joint design has been mostly finished and will be planning to submit to hopefully the Journal of Mechanical Design. And then I co-authored a paper with Brandon Sargent and Jared Butler on an origami catheter support tube for intuitive surgical. And my work helped result in 6 invention disclosures, and those are disclosures that get sent off to the tech transfer office for BYU, who then gives it to lawyers that write it up into a patent. So they're not all, haven't been all filed yet, but they've all been disclosed to the tech transfer office. But one on the second version of the deployable barrier, the last iteration that I showed, and then the catheter support device that I just mentioned. And then 3 for 3 different cylindrical development mechanisms, one that I didn't talk about. And then also an expandable spinal fusion implant, which was a result of a summer burst project from a couple summers ago. So for acknowledgments, the U.S. National Science Foundation and the Air Force Office of Research through the NSF funded the work for the ballistic barrier, and the cylindrical development mechanisms were both funded by an NSF grant, both of those papers and work. So I'd like to thank my wife, Ellie, first and foremost, for sacrificing her educational and personal and work goals to raise our 3 kids while I was going to school. And she'll be going to school when I finish, and I'll pay that back with financially supporting the kids. But I'd also like to thank my parents, Liz and Ken, who both worked for a long time to get me through school and braces and trips to different places and helping with tuition when I moved out here. And so obviously couldn't do this without them. And then my advisors, Dr. Hal, for helping me see what I could accomplish and getting me on the right track to finish my goals, and for keeping his goal to be a mentor first and a professor later is definitely acknowledged. And Dr. Magley for helping me to find my research path when I didn't know where to go, and for demonstrating that work and funds should not be mutually exclusive. And also thanks to Dr. Bowden for introducing me to the wondrous mechanical design of the human body that God created. I'd also like to thank members of the Mechanical Design Collective and the CMR for all their help. I think everyone here, in a way, contributed to part of my work, and I wouldn't be able to do it without the many projects that helped to facilitate, concepts and designs for this work that I later did analysis on. And of course, Heavenly Father and Jesus Christ, because I wouldn't be half of the man or engineer that I am without inspiration and guidance from them. But before I close, I wanted to show a little bit of independent work that I did. This is a little bit of with a smile. But in the compliant mechanisms research meetings, we often start with a prayer, and Dr. Howe always chooses the person that gives that prayer. And I've been gathering data for about a year or so.
Oh no.
on the position that the prayer giver is in. So you have about a 25% chance of saying the prayer if you sit at a 90-degree angle to him. 50% chance if you sit in the 3 chairs at a 45-degree angle from him. And about 1 in 10 times he'll go to the person 3 steps away and ask them to pray. So.
Wow.
So just a little bit of a reminder that you should have fun when you're working. So that's it for my presentation today. So thank you.
Question about the surgical dope mechanisms. How did you come up with those functions that you wanted to attack? Because it seems like you had a lot there. How did you choose those ones that you ended up using?
You mean the big chart?
Yeah. Because it seems like you have a lot more than just cut and
right. Yeah. So this was
expand, right?
the functions list was
those ones that you actually ended up doing.
So good question. I did not. This wasn't the goal to reach all of these. The functions list was just a non-expansive summary of things that these could accomplish. So there are mechanisms that we are aware that might be able to accomplish all of these. So it's just a way to help the designer think about what you might be able to accomplish and then modify these. But just give you an idea of the end goal of these, what these things could do. Because you see one, you go, oh cool, that opens up. But this might get you brainstorming about other things that motion or other motions could accomplish.
Yeah, but how did you choose the ones that you ended up doing?
Oh, based off of a summer burst project, these mechanisms were developed, and we had a lot of different mechanism types sketched up, and with input from professors and some personnel at hospitals, we decided on basically made a pew chart of these mechanisms and what we hope them to accomplish, and down selected to the 3 most promising and feasible mechanisms and went with those functions. Sure.
So I don't remember where it's your angular to square cross-section beams. You had a plot that you had the 2 curves fit against each other. Oh, I don't remember where it is. It's not this plot, it's a later plot.
The last plot.
Yeah, that guy right there.
Yeah.
I just want to, so this is your fitted curve, your dashed line to your data?
So sorry, the straight line is just the curve fitted to the different models that were analyzed in FEA. So there was no analysis to fill those values. It's just a fitted curve to the FEA models.
So in your plot you have this your thickness to radius from 0.03 to 0.09. Why did you select that range? And did you investigate anything outside of that? Because it seems like your dashed line is kind of like coming in on top of your other line, and you could get some pretty extreme values if you move outside of that.
Exactly. So for example, this is the ratio for the FEA model that I made, 0.05. But this is just the feasible range of manufacturing limits, because once you get this small, it just becomes too thin to create anything. And then beyond that size, there aren't many materials that can sustain that amount of stress because it gets too thick to deflect. So those are the 2 end stops there on the scale. So yeah, those diverged quite thoroughly after that.